This is the outline for chapter 32. So few lines, quite a lot, but we'll first talk about the Gauss law for the magnetic field, so which will be the fourth equation or the fourth law in the Maxwell equation. And then also we will talk about the induced magnetic field and also the displacement current. Actually, this displacement current is related to the Ampere's law. So actually in chapter 29, when we talk about the Ampere's law, we only have one term on the right side, which is the enclosed current within the Ampere loop. But for the complete Ampere's law, or in this textbook, it calls it the Ampere Maxwell's law. So which include another term, and that term is corresponds to the displacement current. So here we will also talk about this displacement current. And then below there are 1, 2, 3, 4, 5, but actually I consider them as some hardcore physics stuff. So I think it is very difficult to imagine what it is. So just let you know some phenomenon, hardcore physics phenomenon. And so you can just feel like you listen to a story. Okay, so here we talk about the Gauss law for magnetic fields. Gauss law for magnetic fields. So in chapter 23, we already learned the Gauss law for electric field. And actually how we apply this Gauss law are actually the same. So of course, we have the Gaussian surface. For example, this one, the red one, or this another one. So here it says the simplest magnetic structure that can exist is the magnetic dipole. So magnetic monopole does not exist, and this is what we have mentioned before. So for charges, we can have positive charge, negative charge to be exist independently. But for magnetic structure, we can only have a magnetic dipole. We cannot have a magnetic monopole, just like a primary student can know. If you have a magnet bar, then if you try to cut it into 2 parts or 3 parts, then this is north pole, this is south pole, and then for the smaller one, they will also have the north pole and south poles pair individually. So you can never ever try to make it a monopole, only consists of a north pole or only consists of a south pole. So here it says the Gauss law for magnetic field is a formal way of saying that magnetic monopole do not exist. Magnetic monopole do not exist. So the law assesses that the net magnetic flux phi b through any closed Gaussian surface is 0. So similar to what we have learned in chapter 23, we have something like phi e is the surface integral, the closed surface integrals of E dot dA, something like that. So we have epsilon naught integration sign, something like this, and then E dot dA equals Q enclosed, something like that, if you don't really remember. So here rather than having E on the left side, we have a B for the magnetic field. And actually at that time we can have individual charges. We can have positive charge or negative charges to exist independently. But here we can't have this kind of monopole, magnetic monopole. So in this case, on the right side, rather having a Q enclosed, we can have a magnetic monopole on the right hand side. So for the dipole, when you consider a dipole, and then you consider the total dipole, then it will be a 0, because when you just similar to what we consider as a electric dipole. Actually, the charge can exist independently, but yeah, also the charge can exist as a electric dipole. So when you consider an electric dipole, the total charge is still 0. So as this case, so we consider for the Gauss law for magnetic field, we have a 0 on the right side. Okay, and actually, as I mentioned before, there are derivative between the equation for the E field and the equation for the B field. So actually, we need to change E to B, and we need to change epsilon naught to 1 over mu naught. But yeah, so actually, if we consider like that, then it should be something like 1 over mu naught and then integration of a B dot dA equals 0. But actually this one is already 0, so if you multiply mu 0 on both sides, then it still holds. So finally it becomes like this. We don't have the mu naught on the left side. Okay, so this is what we have seen in the chapter 33. So Gauss law for magnetic field says that there can be no net magnetic flux through the surface because there can be no net magnetic charges. Yeah, magnetic charges in quotation. So individual magnetic poles are enclosed by the surface. So yeah, so this is actually the fourth law for the Maxwell equation. And yeah, and actually we don't need to talk too much about it because you have already learned how to use the Gauss law for electric field. So the usage for this one is similar and even easier because we don't have we only have a 0 on the right side. So you only need to deal with the integration on the left side. But yeah, actually you already know how to do that. Okay, so this is the next part, which is about the induced magnetic field. So in chapter 29, we only learned something like integration of a B dot ds equals mu 0 I enclosed, something like that. Yeah. Okay, so this is so-called the Ampere's law. Ampere's law. Okay, so here, yeah, on the left side it is actually the same, but on the right side is different. So let's take a look at what it is. So here it says a charging electric flux induce a magnetic field B, called the Maxwell's law. So this one called the Ampere's law. This one called the Maxwell's law. Actually, in this textbook, it separates the Ampere's law into Ampere's law and then Maxwell's law, and then when you add the right hand side term together, then the textbook call it the Ampere-Maxwell's law. But yes, for some other literature, it just tell you the whole thing is the Ampere's law. So yeah, yes, actually this is the first time I see someone calls, this is Maxwell's law. Yeah, but anyway, so here on the left side it is still the line integration of the B field, and on the right side it is mu naught epsilon naught. So this is the two constant. This is the permittivity constant. This is the permeability constant. So they multiply together, and then here we have the time derivative of the dE. So it reminds you something about the Faraday's law, because for the Faraday's law, when you have a magnetic flux changing, then it will induce some EMF. But here, when we have some E field or electric flux changing, then it will induce some magnetic field. So it feels like if you have a changing E field, it will generate B field, and then if you have a changing B field, it will generate E field, something like that. Okay, so here relates the magnetic field induced along a closed loop to the changing electric flux phi E through the loop. So yeah, so it will be something like that. And I suppose you also know or how to apply it, because for the Faraday's law, you already know when we have a changing magnetic field. So it would be like something like this: E dot ds equals negative n d phi b dt, something like that. So this is the Faraday's law, this is the Maxwell's law here. Okay, so yeah. So here it says charging a capacitor. So as an example of this sort of induction, we consider the charging of a parallel plate capacitor with a circular plate. So this is the parallel plate capacitor, and then the shape for the parallel plate is a circle. So yeah, so the charge on our capacitor is being increased at steady rate by a constant current I in the connecting wires. So it assumes that this is a capacitor, and there is a constant current charging this capacitor. So as you know, I is actually dq dt, which means that if there is some current going in this left plate, then there will be charges accumulating on the left plate. There will be positive charge accumulating on the left plate, and there will be negative charge accumulating on the right plate as well. So, and if you still remember, for the capacitor, we have the equation as Q equals CV. So if Q is increasing, the voltage or the potential difference between the two plates are also increasing. And also the E field from the positive plate to the negative plate is also increasing. So which means that when you consider the cross-section area, you consider the electric flux. The electric flux is also increasing in a constant rate. Okay. So yeah, so increase at a steady rate by a constant current I in the connecting wire. Then the electric field magnitude between the plates must also be increasing at a steady rate. So which means that here, when we have a constant current, then the Q is increasing. The Q is increasing, the potential difference is also increasing. And then when V is increasing, E is also increasing. Then E times A equals the phi E is also increasing in a steady rate, because all of them are just so this is Q increasing constantly, and then Q equals ZV, so this is linearly increased, so this is also linearly increased. And then E equals VD, so this is increased linearly, this is also increased linearly. And then phi E equals EA, so this one increased linearly, this one is also increased linearly. Okay, so yeah, so here we come up with that the phi E is also increasing linearly. So when we take the time derivative, it is a positive constant, and then it makes this one is also a positive constant. And in that case, okay, so this is the cross section here, here, and then you can see the cross means the E field is pointing into the page, It's pointing into the page, which means that you're actually looking from right to left, because left to right. Actually, the E field is pointing to the right side. So here is the cross section. You see the cross, which means that you see from the left to right. You see it in this direction for this figure. Okay, so in this case, the E field is increasing. It will generate the B field in this direction. So in this figure, it is clockwise. So actually, it just follow the right-hand rule. So you use your thumb pointing into the page, follow the direction of the E field, and then your forefinger will just follow the direction of the B field. So it also satisfies the right-hand rule. Okay. So next, so here continues. The E field is direct into the page. Consider a circular loop through point 1. So this point is point 1. A loop that is concentric with the capacitor plate and has a radius smaller than that of a plate. Which means that it refers to this Amperean loop. Okay. So because the E field through the loop is changing, the electric flux through the loop must also be changing. According to the above equation, this changing electric flux induces a magnetic field around the loop. Okay. So here you try to compare this so-called the Maxwell's law with the Faraday's law. So here we have changing electric flux. It will generate magnetic field. And here we have changing magnetic flux, or changing magnetic flux. It will generate induced E field, induced E field or induced EMF. Okay, so they look quite similar, but there are some difference. So they are similar but different in two ways. So first is that mu0 and epsilon 0 appear for matching the SI unit. So the first point is that here we have these terms, these two constant here, these two terms here, so that the SI unit will match. And in the next chapter, I will, I can just let you know here. These two constants multiplied together is a very important constant, or I can write it as C equals 1 over square root of mu naught epsilon naught. So this C is so-called the speed of light. Speed of light. 光速. Speed of light. So C equals 1 over square root of mu naught epsilon naught. For just a normal person, we only need to know C is 3 times 10 to the 8th power meter per second, then it is quite enough. And actually, if you need to learn something about the optics or special relativity or whatever, then probably you need to know the C up to 4 digits, something like 2.998 times 10 to the 8th meter per second, something like that. Okay, so this is the speed of light. So actually this permeability constant and permittivity constant are related to the speed of light. And in the next chapter, I also let you know or see, actually the light is a type of the electromagnetic wave. Okay. Okay, so this is the first different point, and then the second one is that the negative sign here, the negative sign for the Faraday's law. So the negative sign for the Faraday's law means the induced electric field is counterclockwise if the magnetic field direct into the page and is increasing. So it means that here is for the Maxwell's law. So when we have E field is pointing into the page and increasing, the induced B field should follow the right hand rule. So you use your thumb pointing into the page, and then your four fingers, your thumb pointing into the page, and then your four fingers will just follow the direction of the B field, the induced B field. And here we have the negative sign for the Faraday's law, which means that if we have B field pointing into the page and is increasing, then still it follows the right hand rule but without the negative sign. So which means that d phi b dt is into the page. So you use your thumb pointing into the page, your forefinger is follow this direction, but as much as we have a negative sign, so the E field should be counterclockwise. So these are the 2 points differentiating the Maxwell law and the Faraday's law. One is this constant, and another one is the negative sign referring to the opposite direction of the induced B field and E field. And of course, the main difference is that here the Maxwell's law is changing E field, generating B field, and here changing B field, generating E field. Okay, so up to here we know there are 2 laws. One is called the Maxwell's law. In chapter 29, you know, this line integration equals mu naught I enclosed. And also we know the Maxwell's law in this chapter. The same line integration equals mu naught epsilon naught times the time derivative of the electric flux. Okay, so here I said why not both? So here we relate the magnetic flux induced along the closed loop to the changing electric flux through the loop. So we can just put them together. On the left side, we still have this line integration for the B field, and on the right side, we have this term here and then this term here. So this one is called the Ampere's Maxwell's law. So when there is a current, so now we don't need to worry about which one we should refer to. We can just put them out, and then we consider which one is zero, which one is non-zero, or maybe sometimes both of them are non-zero. So that's why it's better for us to put both terms out. But when you just do the exercise in chapter 29, and then you can clearly see that there is no changing E field, then you can directly just ignoring this term. But and here, if you can see or something, there is no static current, then you can just direct current cross out this term. But it might be a better idea to first write out the whole thing, and then you consider one by one whether it's zero, and then you try to cross it out. So when there is a current but no change in electric flux, such as a wire carrying a constant current, the first term on the right side of the equation is 0. And so the equation reduced to I think this one should be the second term rather than first term. The second term of the right side of the equation is 0, and so the equation reduced to Ampere's law. And then this is the first. Okay, so and the second point is when there is a change in electric flux but no current, such as inside or outside the gap of the charges of a charging capacitor, the first term on the right side of the equation is 0, and so the equation reduces to Maxwell's law of induction. Okay, so that's how we determine whether either of them is 0, and then if one of them is non-zero, then there will be some induced B field. Okay, so far any questions? Okay, so let's take a look at this sample problem. Okay, so it says a parallel plate capacitor with a circular plate of radius r is being charged. So this is what we have mentioned, and derive an expression for the magnetic field at radius r. So suppose this one is r. This one is r. For the magnetic field at radius r, for the case small r is smaller or equal to capital R. Capital R is the radius of the capacitor. Okay, so here we don't have any okay, so far we don't have any static current, so we can directly apply the law of the Maxwell's law. I mean the induction law of Maxwell. Okay, the Maxwell's law. So actually we can just write out the line integration of a B dot ds equals mu naught epsilon naught d phi e dt. So this is the Maxwell's law. And similar to what we have done before, this B dot ds should point to the same direction. So B dot ds becomes B times ds. So it becomes the closed line integration B ds, and then it should be something like a B times 2 pi small r. So this is what we have done before, so I don't try to explain it again. And on the right side, we have E. We have E is increasing, and of course here we consider the E field is pointing into the page, so it is parallel to dA. dA also pointing into the page because it is just a circle, and then so according to the right hand rule, the path is clockwise. The path is clockwise, so dA should be pointing into the page. Okay, so here we have phi e should be E times A. Because we already assumed that E and A are parallel. E and A are parallel, and E is uniform over the whole area. So actually it should be equal to this surface integration. Okay, so we can just put it EA into here. So we have a mu naught epsilon naught equals d E times A dt. And of course, A is a constant. So we can also factor out A. So we have a dE dt inside. dE dt. Okay, so for this A, it is a circle. So this A is nothing but pi r squared. So we have a B times 2 pi r equals mu naught epsilon naught and then pi r squared and then dE dt. So we can just move over these terms and then we can have the expression of B, which is actually we can just cancel some of the terms. This pi and this pi can be cancelled. This r and this r can be cancelled. And then that's it. So we have mu naught epsilon naught r over 2 and then times dE dt. Okay, so far the question doesn't tell you how does the E field change, so we just put that term there. Okay. So next it asks you to evaluate the field magnitude B for R equals to capital R over 5, which is 11 mm, 11 millimeter. And then dE dt is 1.5 times 10 to the 12 volt per meter per second. Volt per meter per second. Yeah. The whole thing we'll see. Yeah. So in that case, yeah. So actually, we just need to substitute the number into the expression we just obtained. So B equals mu naught epsilon naught R over 2 and then times dE dt. Okay, then we can just plug in the number. Mu naught is 4 pi times 10 to minus 7 and then times epsilon naught is 8.85 times 10 to minus 12 and then R is this one. R is 11 millimeter, 11 times 10 to minus third power all over 2. And then times this one is dE dt is 1.5 times 10 to the 12. 1.5 times 10 to the 12. Okay, so this is 9.18 times 10 to a negative 8 Tesla. Okay. So for part C, it asks you to derive an expression for the magnetic field at the radius r, which is larger than r. So here we consider an amperance loop. This is the r. Okay, so actually we also apply the Maxwell's law. Mu naught epsilon naught d phi e dt. Okay. So on the left side it is still b times 2 pi r. So nothing special on the left side. And then on the right side it is still mu naught epsilon naught times a dE dt. But here the A is not pi small r squared anymore. This A should be pi capital R squared. Because out of this region, we assume there is no E field. There's no E field. Yeah, we assume the fringe E field is totally zero. The fringe effect is zero. So A is only pi capital R squared. So here we have mu naught epsilon naught pi capital R square dE dt. And here b dot b times 2 pi small r. Okay, so also we move over this term, so we have a b equals. Actually, we can still cancel the pi, cancel the pi. Okay, so here we have mu naught epsilon naught capital R square over 2 times small r, and then times dE dt. Something like this. Okay, so here outside it is inversely proportional to the radius. Here inside, so this is r is smaller or equal to capital R. So b, the magnitude of the b field is proportional to the radius. Here r is larger than capital R, so it is inversely proportional to r. So which field lies something like this, So for this part, this is b, this is r. So this is proportional to small r. This part is inversely proportional to r. And this is capital R. So far, any questions? Okay, so maybe let's have a 15 minutes break first.